Muy buenas tardes, mi nombre es Víctor Manuel Trejos y les damos la más cordial bienvenida al ciclo de seminarios 26P del Departamento de Química de la Universidad Autónoma Metropolitana, Unidad Iztapalapa. Agradecemos la presencia de quienes nos acompañan en el salón R206, así como quienes siguen esta transmisión a través del canal de YouTube del Departamento de Química. Antes de dar inicio a la conferencia de esta tarde, compartimos con ustedes algunos avisos de interés. Invitamos a la comunidad a participar del ciclo de seminarios del Departamento de Química, coordinado por el doctor Ricardo Atahualpa Peralta Ávila y la doctora Dafne Saradía Guzmán Hernández. De igual manera, extendemos una cordial invitación a colaborar en la Gaceta Telecachil, coordinada por el doctor Gregorio Guzmán González, la doctora Gabriela Valdés Ramírez y el doctor Aldo Román Camacho, y el doctor Jorge Garza Holguín. En pantalla pueden consultar los datos de contacto y el enlace correspondiente. Asimismo, los invitamos a sumarse al podcast del Departamento de Química, el cual se encuentra a cargo de la doctora Lucero González Sebastián, la doctora Mónica Ledesma Motolinia, el doctor Alexander Pérez de la Luz y el doctor Luis Adrián Ramírez Montoya. La información de contacto se encuentra disponible en pantalla. También los invitamos a seguir las redes sociales del Departamento de Química en YouTube, Facebook, Instagram y X, así como visitar la página institucional. Estos espacios son gestionados por el doctor José Luis Ortiz Quiñones, el doctor Luis Fernando Cofas, el doctor Ángel Alejandro García Chong y su servidor, el doctor Víctor Manuel Trejos. Agradecemos el apoyo de nuestro patrocinador oficial, Estudios Farmacoeconómicos S.A. de CB. A continuación, tenemos el gusto de recibir al profesor Jean-Philippe Bouloin del Instituto Carmine UM 6064 de la Universidad de Rouen, Francia, de quien leeré una breve semblanza. El doctor Samuel Jean-Philippe Bouloin obtuvo el grado de doctor en Química Orgánica de la Universidad Católica de Louvain, en Bélgica, donde desarrolló una investigación enfocada en la síntesis y reactividad del 3-trifluoroacetil lactamas. Posteriormente, realizó 2 estancias postdoctorales en Francia. La primera tuvo lugar en el Institut of Chimie des Substances Naturales, CNRS, bajo la supervisión del profesor Potier y el doctor Xu, donde trabajó en química de productos naturales y síntesis orgánica. La segunda se llevó a cabo en el Leeds Grosgreen Chemie Research de la Universidad Joseph Fourier bajo la dirección del doctor A. Grosgreen, fortaleciendo su experiencia en síntesis orgánica y metodologías sintéticas avanzadas. Desde 2004 se desempeña como profesor de química orgánica en la Universidad de Rouen, Normandía, Francia, donde desarrolla actividades de docencia e investigación en el área de síntesis orgánica. A lo largo de su trayectoria académica ha publicado más de 146 artículos científicos en revistas internacionales arbitradas e indexadas. Es coautor de 2 libros de docencia y cuenta con 3 patentes relacionadas con sus líneas de investigación. En el ámbito de la formación de recursos humanos ha dirigido 15 tesis doctorales, de las cuales 4 se encuentran actualmente en desarrollo, dentro de proyectos financiados por la BEX, CINORC, Crunch y la Agencia Nacional de Research, INR. Asimismo, ha supervisado 8 estancias postdoctorales, 3 en la Universidad de Reims y 5 en la Universidad de Rouen, contribuyendo de manera significativa a la formación de investigadores en química orgánica. So, thank you very much, everyone. I will to continue in English. First, I would like to thank Professor Jean-Philippe for being here. So, Professor Jean-Philippe, go ahead with your presentation. So, the table is yours.
Okay, thank you very much. Did you heard me? No problem. Okay, so first of all, I would like to thank your university, and also I would like to thank Eduardo, Alexandro, to be welcome here, and also I would like also to thank ECOS project, because in fact I was here due to this project. So today I will present you rhodium-catalyzed hydrosilylation in the two different topics. The first one deals with the trifluoromethyl alkenes, and the second one deals with 1,1-disubstituted enamide. So my topic deal with a different topic, different part. The first of all, I would like to present you an introduction. Then I will focus regarding some kind of hydrofunctionalization of two trifluoromethyl alkenes. The second is my first topic. The third topic deal with the asymmetric rhodium-catalyzed hydrosilylation, and then I will conclude. So, first of all, organic carbon are very important in organic synthesis, and in fact, what could be interesting if we deal with the synthesis of silylated compound, it is important to compare carbon and silicon. And in fact, if we compare carbon and silicon, you can see that there is different kind of properties. For example, if you compare here the carbon regarding the radium covalence, and here you can see that here the radius covalence is really higher. You can see also regarding the bond length, you can see that the bond length with the silicon carbon are really longer, and also regarding the electronegativity, which is very important. So it is a reduce of electronegativity. So now, taking into account that properties, to put silicon into organomolecules, it brings some unique properties, and especially these 3 points, which is very interesting. The first point, they could be increase the lipophilicity and also increase the metabolic stability. So now, regarding the organosilicon, so organosilicon is very important in different fields. The first field deal with the organochemistry. For example, here I show you what we call Karlstedt catalyst. This catalyst is very important regarding hydrosilylation reaction. The second one deal with this kind of medicinal chemistry. And as you can see here in that scheme, that by replacing the carbon with, for example, here this kind of silan diol, we can replace here the carbonyl function. And this is very important regarding some kind of biological application. And third, so organosilicon is very interesting regarding so kind of material science, and especially here I just focus regarding that kind of compound which is called D4, and D4 it's a raw material which is very interesting regarding silicon ore. So it means that organosilicon compounds are very important in general. So now I would like to focus regarding so organosilicon, the way to prepare that kind of compound, and in fact there are a lot of methods. So I just would like to briefly present you a few methods. The first most general means the reaction in the presence of a Grignard reagent, of this type, and we can lead to organosilicon compound. Second one deals with the alcohol as a starting material. We can perform cross-dehydrogenative coupling in the presence of hydrosilane to obtain the final compound. The third method deals with the silylation using unsaturated compound, and in that field, in fact, we manage the reagent using silicon boron and silicon halogenic derivative. The third one deals with the carbene insertion starting from this kind of diazo compound and then reacting by hydrosilanes, we can lead to organosilicon compound. The last one, direct, this method is really more recent, could be included direct CH bond silylation starting from carbon sp2 and carbon sp3 to obtain the final compound. And this, okay, and the more interesting reaction is that one, and we will deal with that kind of reaction, deal with the hydrosilylation of alkenes using hydrosilylation. And we will focus mainly on that kind of reaction. So regarding, so now focusing to hydrosilylation reaction, in fact, they could be done in different compounds. First, for example, they can react in the presence of mono alkenes derivatives, and we can obtain different kind of silated compounds. So I will go back to that kind of mixture later during my presentation. We can also perform hydrosilylation in 1,2 alkenes derivatives to obtain the corresponding silanes derivative. It was also possible to perform the hydrosilylation of cyclic 1,3-dienes, and you can obtain like this the compound which is cycles, and also you can see that in that position we have a kind of asymmetric centers. And we were focused regarding that kind of compound. So this is the hydrosilylation of 1,1 alkenes, and in fact it could lead to 2 compounds. This is called what we call Markovnikov product, and this is anti-Markovnikov product. And if you look on the literature, in fact this reaction is really less known, and in fact it's very limited to very simple substrates, especially substrates containing alkyl and aryl derivative. And we will focus regarding that kind of topic. So what is the deal of our project? It was as this. Because in fact in our lab we were interested regarding fluorinated derivative, we would like to perform the reaction with 1,1-trifluoromethyl alkenes, and we would like to do 2 things. First, to do hydrosilylation reaction to obtain kind of silated fluorinated derivative. And the challenge was this. First, we would like to obtain chemoselective reaction. Secondly, we would like to obtain regioselective reaction. And what it is very important, we would like to avoid the elimination of fluoride, because usually we can have sometimes have the elimination of fluoride, and then we can obtain the double bond with CF2. In the second part, we would like to do hydrogenation reaction to obtain this kind of saturated derivative. So, before to start my presentation, I would like to give you a quick state of the art regarding the synthesis of trifluoromethyl silane. In fact, in general, there is 3 different methods. So, the first one deal with the Grignard reaction. In fact, there was 2 reports, so it is mentioned here. And in fact, we will do the reaction with this kind of trifluoromethyl ketones in the presence of Grignard reagents to obtain that kind of compound. The second one deal with the carbon insertion, and in that there is really more reports. We start with that kind of compound, so pay attention because that kind of diazo compound sometimes is not very stable. And then it can react with hydrosilane in the presence of different kind of metals to obtain that kind of final products. By regarding these 2 methods, there is 2 drawbacks, and the drawbacks are this one. First, if you look at, in fact, they are really very strict conditions, and also there is a kind of limitation regarding the scope substrate. The third reaction deal with hydrosilylation reaction, starting with fluorinated alkenes in the presence of hydrosilanes. It could be done in different kind of metal catalyst, and as you can see here, we will be able to obtain different kind of compounds. So what it means, regarding that kind of strategy, in fact, we have to focus on chemoselective reaction to obtain only 1 compound. We would like also to perform regioselective, and what we would like be interesting, it will be devoted to such a kind of compound, because this kind of compound really usually are less known. And as you can see, also there are asymmetric center on that molecules. So we would like also to perform enantioselective version without elimination of the fluoride. In fact, we don't want to obtain that kind of compound. So now focusing to hydrosilylation reaction, I just would like to give you 3 or 4 reactions. So this reaction is known, Okay, but there is some limitation, and I will show you that. So, for example, Ojima start with this kind of trifluoromethyl alkenes in the presence of ruthenium catalyst. He obtained 5 examples, but as you can see, the yields are really very low. The second one deal with so this is the ruthenium, this is the platinum derivative. So there are two kinds of author which is working on that. It is Marty and Lay and Pang. So they use the hydrosilylation reaction starting from this trifluoromethyl alkenes in the presence of platinum. And as you can see here, there are only one example of each reaction. And for this reaction, the catalyst means regarding Karlstedt catalyst, which is very known catalyst. And the third one deal with the rhodium in the presence of Marty. So this is probably the more interesting reaction regarding that. But as you can see, also, there's only 5 examples, and the yield is up to 70%. So we can see that it is very limited regarding the scope and also the yield of that kind of reaction. So we decided to use as a model the reaction of this kind of trifluoromethyl alkenes with an half tilt to have a compound which could be enough stable to isolate them in the presence of phenylmethyl hydrosilane. And what kind of compound we can obtain? We can obtain that kind of compound which corresponds to Markovnikov derivative, adduct. This is anti-Markovnikov, and you can also obtain kind of hydrogenation of the double bond. So at the first stage, regarding our parameters, we would be interested regarding the catalyst and the ligands. And as you can see here, with different kind of catalysts, rhodium, palladium, ruthenium, iron, cobalt, nickel. In fact, you can see here that here we have almost no conversion. And in fact, in rhodium catalyst, we were able to obtain 94% yield of conversion. And in fact, we are not obtain all the compound. In fact, this compound we don't obtain, and we obtain these two type of products. And what is very interesting, it means that this kind of hydrosilylation compound is the major product. So what we would like to perform, we would like to perform and to use other kind of parameters to try to improve the yield of that kind of compound. Okay, so here I just presented only in one slide, but the optimization was really quite long. So we try to use the best rhodium ligand catalyst. You can see here that we have several catalysts, and in fact, it was really the more interesting using rhodium COT Cl in the presence of kind of phosphine. Then we try to screen the solvent, and in fact, these two values are interesting. So regarding hydrosilylation reaction, this ether was the more interesting solvent, but you have to be careful about the ethanol because I will go back to the reaction in the presence of ethanol. Regarding the concentration, so we use different kind of concentration, and the best yield was obtained with this kind of value. And regarding the temperature, so we did the reaction at room temperature, at different temperature, and the best one corresponds to that one. Using this kind of parameters, okay, in pink or red, I don't know exactly the color, okay, in fact, yes, the time, sorry, the time we use mainly 20 hours to do our reaction. So it means using such a kind of parameters, we were able to obtain this kind of final product without this one on 76% of isolated yield. So using that, we would like to perform the scope of our reaction. I would like to show you what we are able to obtain for the final compound. So we can replace this naphthyl group by the phenyl, you can see that the yields are exactly the same. We can concentrate on aromatic having electron donating group or electron withdrawing group. So you can see here that having electron donating group, methyl, on different kind of position in parameta and ortho position, also as a methoxy derivative, the yield was really correct. We were able also to perform the reaction using the chlorine derivative. So this is interesting, especially if you would like to do post-functionalization reaction. For example, you can do after, when you obtain this product, to do, for example, kind of Suzuki coupling or other things. The reaction was also possible in the presence of electron withdrawing group. As you can see, the yields are a little bit lower, but it could be correct. We do the reaction with the diphenyl derivative. Also, what could be interesting, it is possible to do the reaction in the presence of an aromatic, in the presence of free hydroxyl group, which is normally not so easy. And also, of course, you can see that the yield drop down, but when we protect this hydroxide with a kind of basyl derivative, the yield increase. We were also able to do the reaction in the presence of heterocycles, which is very interesting. So we perform the reaction in the presence of two baso derivatives, also in a free quinoline. The reaction was also possible in the presence of alkyl derivative, and we were also able to use our reaction playing with a long chain. For example, we were able to obtain this kind of derivative with C2F5, just to show you the scope of the reaction. But in fact, there are also some limitations. For example, we would like to perform the reaction without using the fluorinated substituent. And as you can see, if you compare, for example, this one with that one, you can see here that the trifluoromethyl are very influence on the reaction. And also, that kind of substrate, it is not possible to obtain the final compound. So now I just would like to propose you a mechanism for such a kind of reaction. So the complex A, it is really the complex which we start our catalytic cycles. Then we obtain an SEH bond activation in the presence of hydrosilane to obtain the rhodium-free. And this rhodium-free can just coordinate with the double bond. So taking into account that this alpha position is very enriched, in fact, how could you say, the insertion will deal on the beta position. We obtain such a kind of derivative, and after we can have the insertion. And here there is two kinds of mechanisms. So if you would like, we can go back to that. So there is what we call Schalk-Arrow mechanism or modified Schalk-Arrow mechanism. I think it's not very important now, but we are able to obtain the complex D and E, and after one reductive elimination, we were able to obtain the final compound and then to regenerate our catalyst. It was the proposition. So just to tell you that it's interesting to try to do this reaction, we will do some kind of post-functionalization to see what could be possible to do with our final compound. So starting with that compound, we will be able to replace the phenyl by a fluorine. It is known in the literature with HBF4. Like this, we will be obtained to obtain that kind of compound, and with this compound, we were able to do two kinds of reaction. We can really remove the silicone group using Fleming-Tamor oxidation to obtain that kind of derivatives. And we also can do some kind of substitution of this fluoride in the presentation of lithium 1,3 dithiene to obtain that kind of compound. This compound is interesting because if you trade this compound with a base, you can deprotonate on that position, doing doing the reaction with chlorosilane, we will be able, after hydrolysis, to obtain acylsilanes. And acylsilane is very interesting regarding organosilicone derivatives. Yes. In fact, you see at the beginning, when we did our first reaction, we obtained hydrosilylation compound, but also simply hydrogenation derivative. And we think that probably there was one intermediate which is common in these two reactions. And just by changing ether by the ethanol, in fact, we were able to obtain only the formation of hydrogenation products. So I just would like to give you in two slides a quick optimization to obtain the final derivative. So we use the catalyst that we used before. So the reaction was done at 80 degrees, 12 hours. Okay, we obtained such a kind of yield, but we would like to optimize because in fact the yield was not so very good. So in fact, we simply change the temperature and also the time. And you can see here that in the entry 4, we will be able to obtain quantitative yield. So this is the NMR yield, and in bracket, it's isolated compound. So having this condition in hand, we just would like to show you what could be possible to perform the scope of the reaction. So one thing is important. You can see here there will be in the screen two values, the value in blue and the value in red, because in fact, depending of the size of the substituent, the components are quite volatile. So you use usually the yield by NMR, and when the compound was enough EV, we will be able to isolate them. So it means that it works well in the presence of benzene, but this compound we are not able to isolate. It works well, as I show you, with the naphthyl. It works also very well in the presence of electron withdrawing group, and as you can see, the NMA yield is quantitative, and when you isolate it, we obtain a very quite good yield. It's possible to obtain the chlorine derivative. With the benzene having an electron donating group, it works well. So look, again, when you have the phenyl derivative, we obtain NMR by the yield by NMR, but we are not able to isolate the compound. Even the compound are really bigger. For example, this compound, we will be able to obtain the isolated yield. And we will also able to obtain, for example, here, the compound with 2-benzofurane. And as you can see, the NMA yield and isolated is almost the same. So just, this is my first part, my first project. So it means that using this one of 1,1 disubstituted trifluoromethyl compound by doing the reaction in the presence of rhodium and hydrocatalyst, we were able to obtain this kind of hydrosilane, 30 examples with the yield which is quite good. And then just by changing the ether by the methanol in the presence of octane with hydrosilanes, we will be able to obtain hydrogenated compound. So now I would like to go to the second part. So the second part deal with the asymmetric. So asymmetric, of course, its direction are more interesting, of rhodium catalyst. We will start with this kind of 1,1 enamide by doing the reaction in the presence of hydrosilanes and rhodium. And as I showed you before, we could be able to obtain Markov-Nikov or anti-Markov-Nikov product. In fact, regarding what could be interesting for us, we would like, if it's possible, to obtain only such a kind of anti-Markov-Nikov, because usually these compounds are really not very easy to obtain. So the deal, the challenge is to obtain chemoselective, regioselective, and here enantioselective version, which is, you will see that it was not so easy to obtain. Okay, just to give you a brief introduction regarding what we call chiral alpha amino beta silase. is a compound which could be very interesting. For example, I show you here an example of the compound which is silylated derivative, and without the silicone, it is called cetroxide, and this is a drug regarding the fertility treatment. So regarding the general strategy of alpha amino, beta amino acid, in fact, there are three different. You can do by enzymatic resolution, but if you look about that, the yield really, because in fact, you obtain 50%, and usually the normal yield are around 35%. I have slide about that if you would like to discuss. The second method deal with the asymmetric version using chiral derivative, but for that there is really two drawbacks. The first is that you have to obtain as a chiral auxiliary. Sometimes chiral auxiliary, they have some price, and also they need at least two steps. And of course, because we were interested regarding hydrosilylation, I will focus regarding the second, the third pathway. Just regarding that, so regarding hydrosilylation reaction, what could be interesting regarding that kind of method, in fact, it could be really, we can say, quite general regarding atom economic process. It's a very straightforward reaction, and what could be interesting, if we look some chiral ligands, it could be obtain a stereoselective formation of the final compound. In fact, I just focus now in racemic version, and I just focus after regarding enantioselective version, and you will see that there are really not a lot of method regarding that method. So regarding racemic, there is really more method. I just present you four methods. So the first one deal with the work of Murray, which is relating to the hydrosilylation of this kind of enamide, of 1,2 enamide, in the presence of rhodium-catalyzed. You can see that they obtain only 4 examples. The second one deal with, again, with Murray, so, but it really changed this kind of enamide using a cyclic enamide, and you can see here using the same kind of condition, but you can see that the yield are really very low, and you obtain only 2 examples. Probably the more interesting is the work of Kite-Scrupp, who is focused regarding the 1,2 enamide, again performing the reaction in the rhodium catalyst in BF3, and in that method he will be able to obtain a large number of derivatives. After, it depends on the yield. Sometimes it's 5, sometimes it's really very good. And regarding those reactions, there was only one example of compound with 1,1 enamide, and we were able to obtain only in one example, so that kind of compound. So it means that really that methods are quite interesting to try to search on that field. So now regarding asymmetric, in asymmetric there is only 2 reports. The first one is done by Lee. The Lee report the reaction in 1,2,2, we can say beta-beta disubstituted enamide. And as you can see here, by working with that kind of phosphate, he was able, in the presence of rhodium catalyst, to obtain a very nice example. And if you look here, which is very interesting, diacetyl ratio and also enantiomery ratio was very high. And there's another example, but it is a little bit far from our topic. This is what we call unreactive internal alkenes. You can see here that this double bond is not linked with the amide. It is exactly the same author with the same catalyst, except that he changed the ligands, and he obtained the compound in which you have the silicon in the beta position. If you look here, you have the silicon in the alpha position near the nitrogen. Okay, so what it means that regarding chiral alpha amino beta silane, in fact there is only not a lot of methods. So we would like to perform some reaction regarding that. So we use as a model reaction this kind of compound as 1,1 desubstituted, and we use the catalyst which was performed by the author before. Okay, it was possible to obtain these two kinds of silylated derivative, and as you can see, we will only obtain that kind of anti-Markovnikov product. We start with the rhodium derivative, and in the presence of this kind of binyl phosphate, and in that we obtain a full conversion. We did not obtain such a kind of compound, and we isolate this compound in 73%. But as you can see here, enantiomery ratio are really not very good at all. So what we would like to perform other reaction, changing different silane, changing the ligands, and as you can see on this screen, the more interesting reaction is that one. So what we would like to use that kind of rhodium, try to go to other kind of rhodium derivative, and also use different kind of ligands to try to obtain a better enantiomeric excess. Okay, so if you look here, so this is the starting, exactly the result that we obtained in the slide before. We perform a lot of reaction of rhodium-catalyzed, and in fact, as you can see here, the yield are really lower in comparison with the yield that we obtained before, and also regarding the enantiomeric ratio, it was not very interesting. So we will focus regarding this kind of rhodium catalysts, and we would like to screen other parameters of the reaction. Yes, before that, we were interested regarding to change the ligands. So this is really the compound that we had before, okay? We go to other kind of ligands. We work with Tadol derivative, with other things. If you look here, the yields are very nice. But if you compare regarding the enantiomeric ratio, it's not good at all, it's 0, okay? Then we focus regarding that kind of biphosphine ligand, like this and like that. And you can see here, there's no reaction at all. Then by playing with palladium nitrogen bidentate, again, no reaction. And then we would like to perform more complex derivative, more complex ligand. And as you can see, again, the yield was marvelous, but enantiomeric ratio, it's 0. Okay, so it means that regarding that, we will really focus regarding that kind of binyl derivative and try to modify it to obtain a better enantiomeric ratio. So the first thing that we would like to, if you look here, we would like just to replace the phenyl derivative using, for example, here, a naphthyl derivative. And just by changing that, the enantiomeric ratio increases a lot. Then we would like to search if could be possible to, we would like to change if could be possible to change the backbone, and especially to work with paraphosphine, this kind of paraphosphine, this kind of paraphosphine. And as you can see, the yield here could be very interesting. And if you look by the result that we obtained before, here the enantiomeric ratio was better. So we are focusing on that thing. So now I just would like to show you how it was possible to try to modify such a kind of ligand to try to increase the enantiomeric ratio. We go to use different parameters, and here I just summarize very quickly. We change the additive, we change the solvent, we change the temperature. So I just give you very briefly. Then by changing the solvent, the best is just to use 1,4-dioxane. When we try to use additive, because usually you are using hydrosilylation reaction, you can add some kind of hydride or derived coming from the boron. And as you can see here, there is really no interesting. So in fact, we did not add additive in our reaction mixture. And then regarding the time, we try to, because usually enantiomeric excess can really increase when you lower the temperature, and in fact, we just focus on that. So until now, what it is the more interesting, using that kind of ligands, using that kind of parameters, we were able to obtain 99% quantitative yield with the ratio of 85 to 15 ratio. But in fact, it's not so nice. We would like at least to increase a little bit. So what we have to do? In fact, we would like just to replace some substituent on that kind of ligand to try to increase the enantiomeric ratio. And I will show you what we did. So, important, it is the value that we have to try to increase this value. What we try three different things. First, we would like to modify the position in the position 3 of the spiral derivative. It means by changing the hydrogen by phenyl, by methyl with different substituent here. In fact, you can see that the yield really are low and the enantiomeric excess go down. Second part, we would like to evaluate the electronic effect. So it means in the phenyl derivative, we would like to add electron withdrawing substituent or an electron donating substituent. In fact, we work with the trifluoromethyl on ortho and para substituent and ortho and para substituent. And again, as you can see, if you compare with that, the yield was really, except for that, the yield here, you can see that the yield was bad and the ratio was not very good. And the last thing that we did, okay, we would like to increase the steric hindrance on this kind of phenyl derivative. And as you can see, we have here the methyl, then we replace by phenyl, isopropyl, terbutyl. And as you can see here, in fact, here we obtain excellent yield, and in fact, we really improve a little bit the ratio. So we finish that because, in fact, we see that we work a lot regarding the synthesis of the ligands. So we decided that this ligand will be the ligand to try to obtain the best condition. So now I would like just to show you the substrate scope. So this is the example that I show you at the beginning. It is possible to put some kind of electron donating substituent, methyl, at different position. And in fact, if you look, when you have the methyl and the ortho position, we were able to obtain 90% with this kind of enantiomeric excess. And just by recrystallization, we were able to obtain 98 to 2, which is quite interesting. Using that kind of compound, we do X-ray diffraction analysis to determine the asymmetric centers. After that, we decided to see if it was possible to increase the steric hindrance. In fact, as you can see here, the yield was correct, but enantiomeric ratio decreased. After, we were interested regarding to put electron donating substituent, if it's a methoxy, 1-methoxy, or different kind of methoxy. You can see the yield was correct, but the E decreased a little bit. We were also able to perform the reaction with S-methyl derivative. Regarding a compound having an electron withdrawing group, it works a lot, but also if you look to that, the yield decreased a little bit. We were also able to perform the reaction in the presence of halogen derivative to do post-functionalization reaction. And then we were interested by combining cyclic derivative. And as you can see, all that value, the yield really are less, and the ratio really was not very nice. Okay, last thing. Yes, last thing. So you can see here, this is possible also to modify the substituent on the amide. So here you can have phenyl, methyl, terbutyl. In fact, As you can see here, when we increase the steric hindrance here, methyl, ethyl, and terbutyl, you see that the yield was correct, but here the enantiomeric ratio decreased. We were also able to change the hydrosilane. It was possible to do direction in the presence of phenyl dimethyl hydrosilane. You can see that the yield was correct. But if we decided to have a more steric hindrance hydrosilane, you can see here that really enantiomeric ratio decreased a lot. So it means that direction is very sensitive regarding the steric hindrance of our silane. Of course, there is a lot of limitation. So first of all, it was not possible to obtain compound here having iodo, bromo, also some trifluoromethyl with C3 only traces. It was not possible to obtain heterocyclic derivative, and this is completely different that we obtained on the first topic. We would like also to do the reaction in a tri-substituted derivative, so adding here a trifluoromethyl or a bridge, and here there is no reaction at all. And what it is very important, and we will see that in the mechanism, if we protect this kind of NH using Bock on basil, in fact, we have no reaction at all. So it means that NH reaction is very important in our reaction. We try to perform the reaction in the presence of carbamate, nothing. And regarding the hydrosilanes, you can see we try to extend different kind of hydrosilanes, and then by doing the reaction with diphenyl terbutyl or diphenyl, we have no reaction. So it means this hydrosilane is very, very important regarding that reaction. So now regarding the mechanism, so we start with this kind of rhodium derivative, having the ligand on the rhodium. So on the first step, we do the oxidative addition in the presence of diphenyl methyl hydrosilanes to obtain the complex A, and then we obtain kind of coordination of our double bond to obtain this kind of rhodium complex. Then we obtain a kind of coordination on the double bond on the rhodium complex to obtain the complex C, and then after a reductive elimination, we were able to obtain this kind of complex in which after, just by simply decoordination, we will be able to obtain the final compound, and then in the presence of diphenyl dimethyl hydrosilane, we will be able to regenerate our cation. So regarding my second topic, okay, this topic deals with asymmetric rhodium-catalyzed hydrosilylation reaction. So we'll be able to obtain around 23 examples of these compounds. So in the yield, which is, you can say, good to excellent, with this kind of ratio, and we were able to obtain 98 to 2 enantiomeric ratio using such a kind of ligand. So it means that we were able to obtain regio and enantiosemeric version, but as you can see, we work a lot to try to obtain good enantiomeric excellence. So now I would like to finish my work by doing some acknowledgement. All this work was done by only one guy, a Chinese guy, so he's called Yuan Ma, with who we did co-tutelle de thèse. So it means it's a thesis share between France and China. So it means that the students stay 18 months in Rouen and then go 18 months in Hangzhou in China. I would like to thank also Samuel, because Samuel, in fact, in our lab all the time, the thesis was done with 2 permanent staff. And so Samuel did a lot of interesting explanation. I would like also to thank my colleague, Li Wengshu. Li Wengshu is the co-director in the Chinese part. I would like also to thank La Région Normandie, because La Région Normandie thanks a lot of money regarding the thesis. And I would like to thank you for your kind attention. Just here, I show you when was the summer and was the sun in Normandy. The lab is doing some acrobranche when we go on the trees something like that. And just last things, just would like just to welcome you in Rouen. So this is the church. This is on the day and this is on the night. So this is a cathedral that is very interesting. This is the place where Jeanne d'Arc was born, and this is also a very nice kind of monument. And thank you very much for your kind attention.
Okay. Thank you.
Sorry? La Seine, La Seine. The river is the Seine. Go to Paris.
Okay. We would like to thank you to Professor Jean-Philippe. So we have time for question, please. So someone have a question? Don't be shy, please.
My computer is messing. No, because if they go to some slide, I prefer to go to the slide. Yes, I think it's more interesting.
I have a question. It's very interesting, your chart. Have you considered biological evaluation or any application of your kind of molecules?
No application at all. In fact, here in the thesis is just to show where there are some drawback in the hydrosilylation reaction, and I show you that it was possible to perform some kind of Pons functionalization, but in fact, our goal was not to apply to go to some biological evaluation.
Thank you.
Other question?
Thank you very much for.
No, it doesn't work. No, I think we can discuss together like that. Is it working?
Hello?
Okay.
Is it working? Is it working? Okay, but is it working?
A little bit, yes.
Is it okay?
Like this.
Okay. Thank you for your beautiful, beautiful talk.
I don't know.
I was remember the first time that I was looking the chemical reactivity of silicon compounds with Professor Correau in Montpellier, 1980, something like this. He was working with substitution reactions with silicon compounds and Grignard compounds. But now I see if we can see your reaction mechanism. Is it possible?
Yes. Which one? The first one or the second one?
The general mechanism, yes. The first one is okay.
The first one, okay?
Yes, I'm really surprised because this is the first time that I saw that the chemical reactivity of the olefine.
1 second.
Okay.
No, it's okay.
Olefine, that the two substituents in the olefine, captodative, I don't know if you have one with electron.
Captodative is
Captodative.
not
No?
captodative. Captodative, you need something which is donating.
Yes, because you have CF3 that is
Electron,
and another donator.
Yes.
It's very interesting. And the other is that the silicon compounds, you have a very soft atom, that is the silicon. And the olefine is very soft. So if you use the HACAB principle, hard soft principle,
Okay.
we work in that.
Okay. I don't know.
The reaction is very good. The
Okay.
problem that you have is that in the olefine, you have two sides to carbon.
Yes.
One is with the two substituents and the other with the hydrogen. And if the problem is electronic, if the problem will be electronic, I don't know, or geometric.
I think it's not electronic. I think it's kind of steric.
Well, it's
Because
geometric.
it's very squared under. So that in fact this part will add to the rhodium-catalyzed and not the other.
Yes,
But
because
it was what we proposed.
no, I was thinking because you need to use all components in a softer way. That means you have using rhodium.
Mhm.
You have this hotness of rhodium. And the solvent, what is the solvent? We can calculate that, it's not
Okay.
problem.
Yeah. But we did not calculate at all. In this topic, we did not calculate. I have another topic regarding hydrosilane in which we calculate, we do DFT, etc. Maybe it will be for the next time. I don't know. But
No.
Here we did
I
not
was
calculate.
thinking using the Lewis thing, the nucleophile, electrophile.
Yes.
And I was surprised because finally the rhodium is the compound, is the atom that make the bond.
Yeah, yes.
Is not the two species
Mm.
that are free
Mhm.
for do the reaction.
But usually, in fact, this mechanism, taking into account what is known regarding hydrosilylation, regarding rhodium-catalyzed, we see that probably we can propose things because usually when you see the hydrosilylation with rhodium, because there are some reaction with rhodium, in fact, we propose that kind of thing. But in fact, we have really, it's a proposition. We have really no special argument regarding that.
If you use another metal, softer metal,
The problem is, as you can see, when you use another metal, because in fact, another question that I have in the previous discussion, it was the problem of rhodium is quite expensive, and we tried other kind of metal catalyst, and as you can see, it doesn't work at all.
oh, just only with the rhodium.
Exactly. If you look, if you look, we try we work with rhodium because in fact Li Wangshu worked with hydrosilylation reaction. So he proposed us to first to do the first atom. And then we try to use other kind of catalyst. Look, palladium, ruthenium, iron, because iron is very interesting, it's not very expensive. Nickel also, but nothing. It's the reason that we use the rhodium.
And how about the solvent?
The solvent, yes, we did. Was I think the next. Oh, yes, but I have to push. I have to put that. Okay. Regarding the solvent, we tried different kind of solvent. Okay. It works. I don't remember. It works. The more interesting it was with ether and THF, that you see that usually we try a lot of solvent and the best was thing like that. Except if you change going to polar solvent and methanol, to completely change the mechanism, we go to hydrogenation derivatives.
Have you think in the eutectic solvent, for example?
No.
I'm really surprised because this chemical reactivity of the silicon is very special.
But you know, regarding hydrosilylation reaction, except that in fact we are able only to obtain anti-Markovnikov product, usually is such a kind of reaction, such a kind of metal.
Because finally, what is the role of the silicon in the reaction?
But what we would like to put the silicone in order to have possible to modify them after. But in fact, it's hydrosilylation, so you have the double bond, and when just would like to add hydrogen and silicone. But there is no really fact regarding the silicone. In fact, just it's hydrosilylation. And then after that, we can move the silicone to, for example, to change the silicone with kind of OH using kind of Tamao derivative reaction, something like that.
Okay, because my guess is that if you increase the soft of the system, you can obtain very good
I think we can have a discussion together. I think. I think.
So thank you. So we have we have time for one question. The last, please.
I think we have a discussion together.
Thank you, Jean-Philippe, for your very nice talk. I have only one question. Yeah, it's okay. It's okay. Number 10 is okay. I would like to know if you explore the acidity between the silicon and the other carbon. For example, you can use as a nucleophilic if you use a basis, different bases to eliminate a proton, for example. Yes,
you would like to on the final?
No, in this compound number 3A,
Yes,
for example.
the final product, yes.
How it is about the acidity of the CH2 near to the silicon? It's
not very acidic.
It's not very acidic because
this is the more acidic one. It's benzylic and phenyl. C3 as
yes,
electron
yes,
with group. You have the benzyl position. I think this is really.
It's not very acidic. Okay.
No, this is very high acidic.
Yes, yes,
not
yes.
that one. Yeah, cool.
Okay. Just to explore a new reaction, what do you think? Maybe you can use it with an ichlophil or maybe.
I think it's just to try to, as I show you regarding post-functionation, to modify such a thing like this to leave the fluorine and to obtain other kind of function. But really, to obtain double bond here, it's not very easy.
It's not very easy. Okay. It was my question.
But maybe we don't try to do, for example, try to put some kind of function here. It could be interesting.
Yeah, just to have a second subject that maybe works in another direction. Maybe, I don't know.
Well, I think not the double bond, but probably try to have a basic here, just
yes,
here, and
right.
then do. But after, for what kind of compound? But
yes,
it could be interesting.
Okay, thank you. Very nice talk.
Thank you.
So thank you, Professor. Okay, you can stop the share, please. Thank you. So thank you again, please. So I'm going to switch to Spanish. Okay, please.
No problem.
Okay, no problem. Okay, thank you, Professor Jean-Philippe. So I'm going to read the. Okay, la constancia. El Departamento de Química de la UAM Iztapalapa otorga la siguiente constancia al doctor Jean-Philippe Boulouin por su participación como seminarista dentro del ciclo de seminarios del Departamento de Química del trimestre 26P con la conferencia titulada Rhodium-catalyzed hydrosilylation of 2,3-fluorine methyl alkenes or 1,1-disubstituted enamides el día miércoles 1 de julio de 2026. Firma el doctor Marcos Esparza Schulz, jefe del Departamento de Química, la doctora Dafne Saraya Guzmán Hernández, coordinadora de seminarios, y Seminario de Química, donde la ciencia nos une. Casa Abierta al Tiempo, Ciudad de México, julio de 2026. Muchas gracias a todos y los esperamos en nuestra próxima edición. Gracias.
Thank you very much.